All right, so now we'll have the chance to hear a talk from Dan Work. So Dan Work is an associate professor of civil and environmental engineering and computer science at Vanderbilt University. He's also interim director for graduate studies and for engineering, and he received a number of honors and awards, such as the Career Award recipient from the National Science Foundation. So today, he will talk about closing the loop on large-scale transportation systems. And Dan, now the floor is yours.
Amaury, thanks for the intro and for all the organization work. It's really a pleasure to be here and see so many folks that have been either directly involved in helping us with the research that I'll showcase today, or indirectly involved in kind of showing some inspiration for how we eventually are thinking about trying to make our transportation smarter, trying to figure out how we can take advantage of all the technology innovations that are happening in mobility that are making this, I think, arguably one of the most exciting times to be working on transportation in the last 120 years. It's transformational right now, and there's such an opportunity for folks like all the folks on this call right now to rethink about our transportation systems and actually push them into scenarios where we want them to be. So I'm going to talk a little bit about how we can close the loop in two direct ways in transportation systems, but I want to also really encourage us to take two steps back maybe and think about the types of traffic congestion problems we're after and what we can do about it. So, at 30,000 feet, of course, in Nashville, like every other city in the United States and many cities around the world, we're constantly looking at these, heat maps of traffic and, thinking about how vehicle automation technologies might eventually, eliminate all of our traffic woes. And this, in my view, is a bit narrow thinking because it kind of imagines a technology solution to a problem that is not entirely technology driven. I do believe that automated vehicles are going to have a dramatic impact on congestion, but whether that impact is positive or negative depends on how the supply and demand shakes out. I mean, at the end of the day, traffic congestion occurs when there is more demand for travel than there is supply. And so, when one tries to figure out what the impacts of automated vehicles will be on the roadway, we can question, what's it going to do to demand? Will it increase? Joan Walker at UC Berkeley did this, what I thought was absolutely a brilliant study called the chauffeur experiment. Well, I don't happen to know of a place where I can go get fleets of brain off vehicles today, but you can fake it by giving people chauffeurs and having the human driver act as an autonomous vehicle. You can give it voice commands and tell them where you want to go, and they can drive you there. And what they did is they did a small scale study and actually gave people these chauffeurs and looked to see whether people took more trips or not. And sure enough, people, when you make things more convenient, easier, more accessible, want more of it. I look at retirees. I think about my parents who are retired. In this cohort, there's a 3 times increase in the amount of vehicle miles traveled in the evening, and those trips are longer. And one could look at that and say, that's more emissions, that's more congestion. But another lens on that is people getting access to things that were not previously having access because they were not comfortable driving vehicles in these types of environments. So we've got to somehow decouple the emissions associated with the demand. But I think there's no question that if you just flat out make driving more convenient or travel by single occupancy vehicles more convenient, you're going to have more vehicle miles traveled. And unless you change the supply of the infrastructure, that is likely to lead to more traffic congestion. The one piece to definitely pay attention to is in the complete brain off world, the ghost trips are the trips that, basically in this study, the chauffeur was told to go pick somebody up, go to the airport and pick up friends or family that are traveling into town. In the future, that might be a trip with a car with nobody inside of it. And you think about traffic being frustrating today, imagine nobody in the car in front of you or beside you. And you can obviously start to imagine the future frustration you may feel. But again, that's only one half of the picture. If you look on the supply side, actually automated vehicle technologies can do pretty remarkable things. This was maybe demonstrated pretty famously in these Berkeley path experiments in the early 2000s that basically connected this fleet of vehicles together, all exchanging wirelessly information about the vehicle state, tracking magnetometers in the roadway so that they were able to drive very, very close together at high rates of speed. And where this became very, I think provocative is you sit there and take those technologies and say, I'm going to literally triple the number of cars that are able to go through a lane of travel by not pouring any more concrete. I'm going to use bits and I'm going to use radios and I'm going to use communication technologies to build a freeway on top of a freeway on top of a freeway without ever having to pour any concrete. That's what tripling the capacity could do. That's what that experiment demonstrated. And you know, in the video that was playing at the bottom, you can see how those technologies have matured to things that Kalle Johansson and his team at KTH have been working on and trying to pioneer those technologies for trucking, where the platooning actually has aerodynamic benefit and can save you fuel and all kinds of other good things. So the takeaway here is that, yeah, actually automated vehicle technologies can significantly increase capacity of the roadways when designed in the right way. And the way that they do that is they exploit this idea of moving people and goods at very high speeds, very close together. You can see this with a little bit of math. I mean, take your toy collection of vehicles that are all driving at some speed V, and they all have some space gap, delta X, between their front bumper and the rear bumper of the vehicle ahead. The vehicles are all at length L. You know, in the basic traffic engineering world, right, you can recognize that the spacing, the front bumper to front bumper distance is just delta X plus L. The spacing is important because in traffic engineering, the inverse of the spacing is the density of traffic, how many vehicles per mile we have, as opposed to how many, you know, feet per vehicle we're occupying. We know what the speed of the vehicles are. They're all driving at the same speed V, and we can look at the flow, the product of the density times the speed, or equivalently, the speed divided by that space gap plus the length of the car. Why am I showing you this stuff? Because if you want to increase the flow on the roadway, there's only three things you can fiddle with. You can fiddle with the speed that the cars move, the space gap between the cars, or how long the vehicles are. And I don't know anything I've seen about suddenly getting cars half as long. So the only real options you have to increase the capacity is by increasing the speed while keeping the space gap fixed, or reducing the space gap while keeping the speed fixed. The video I just showed on the previous slide was a nice example of significantly reducing delta X to get that tripling of the capacity on the roadway. Okay, so you can kind of draw this out into the traffic engineering world and look at these, you know, generic curves that show how the speed of traffic is influenced by the density, or equivalently the inverse spacing. And when the cars are, you know, sparsely collected on the roadway and driven by humans, they all drive at the free flow speed until eventually you get close enough to the cars ahead, you don't actually feel comfortable driving at the same speed, and you start slowing down. And that produces, you know, the classical fundamental diagrams that all have some general shape where as the traffic gets more dense, but the speed is maintained, you get a high flow rate. Eventually it gets too dense, cars start slowing down, and the capacity of the roadway diminishes. So you go back to those drawings and you figure out, I'm going to change delta X, or I'm going to change V, and you can start imagining cars that are automated that leave larger spacings given the same speed could actually be bad for capacity compared to humans, right? We have cars that basically are operating in a less dense regime for a given speed, and that will consequently mean that the flow is reduced compared to humans. Or like in the platooning experiments where the speed was maintained, and relative to human drivers, there were 2 times as many cars on the roadway. That's actually great for capacity. That's exploiting the square footage of the roadway in ways that we haven't done so far. Now, I put all that in perspective, right? We could potentially triple the capacity of the roadway by using all this automation and all this communication. And yet, if you want to double the capacity of the freeway, a simple way you can do it right now is pick up someone else and drive them to work. That would double the capacity of the freeway if everybody did that. Not in terms of vehicles per hour served, but in terms of people per hour served, absolutely. And you know what? If you happen to have a few more friends, you could quadruple the capacity of the freeway by using all the seats in your car. And you start playing this game of like, well, what could you actually do, with bits and, automation and things like this? I don't know. Getting to the 4 or 5x capacity might be at the limit of what might be technologically possible. And yet carpooling makes it trivial to do these things, and certainly in a way that is more environmentally efficient. The Munster Planning Department most famously demonstrated this through these now iconic photos in the planning world, right? You look at the space that's occupied by people on bike, car, bus, you change all the technologies on the car, they're still going to take up the same physical space. And that is actually a fundamental limitation to technologies that improve automation. That's not to say that automation is useless. That's just to say that we need to pick off the right types of problems. And many of the folks on this call, we've all been thinking in a number of very similar lines, looking at these types of phantom traffic jams or instabilities in the flow where a bunch of human drivers doing what human drivers do, trying to do speed control. We make mistakes. Those mistakes get amplified by the cars behind us. We see these phantom traffic jams that appear by their very nature as a result of human driving. And if you get rid of some of the human driving tasks from the human drivers and give them instead to automation, maybe you can do something about it. This was a shot that we got from the Tennessee Department of Transportation Actually, several of the folks in the call are actually in this video. If you look very carefully, you might see some X's on top of some vehicles as they pass through there. The point of that video is basically to showcase that these phantom traffic jams don't just show up on circular tracks and closed parking lots in Japan, but they actually are a feature of most freeways in the United States. It just happens that we don't have drones over all of our freeways, and as a consequence, it's actually relatively difficult to get good quantitative data about these jams. Well, I was very fortunate to work with Benedetto Piccoli, Benny Seibold, Jonathan Sprinkle, and Maria Laura Della Monache on a project for almost 6 years ago now, where we basically took that idea of that ring experiment, replaced it with one automated vehicle on the ring, and basically took a vehicle that went from a black arrow under human control to a red arrow now under vehicle automation, running a variety of different control algorithms that are ultimately trying to pace the vehicles on the ring and eliminate the stop and go feature that the human drivers on the track were there. The key takeaway from this experiment was really proof of concept that a single vehicle controlled in the right way can actually have a dramatic impact on these traffic conditions. And it really builds off of work that, I was very fortunate to work with Alex and Benedetto many years ago, thinking about what one car in 20 could do if you only had GPS in it. You could change the game in traffic estimation. Well, that became true. We're now really rethinking what happens when 1 in 20 cars is able to control the traffic overall, instead of depending on dedicated actuators there. So really important experiment. We'll hear more from folks on this workshop about the technologies required to do that and how expensive and limiting those are. And really, to get to the impact that we want on our freeways, we're going to have to overcome some of those limitations. One of the pathways that we started to think about these limitations as well, if we're just doing longitudinal control or speed control of these vehicles, it might be that the commercial adaptive cruise control systems can already dissipate phantom traffic jams. Widely known in control theory, if you do constant time headway, you should be able to choose the time gap large enough that you should be able to stabilize these traffic conditions and actually eliminate jams. Well, did anybody actually implement those commercially? It was actually hard to find good quantitative data about the performance of commercially implemented adaptive cruise control systems until maybe the last 3 years. Our own team was part of this effort to try to tease out what happens with commercial ACC systems. We know that human drivers create phantom traffic jams. Can adaptive cruise control systems get rid of them, or do they also amplify some types of traffic disturbances? We put a bunch of cars on a roadway, lead vehicle runs a speed disturbance, slows down from 50 miles an hour to about 45 miles per hour, and we check to see if cars running adaptive cruise control following behind amplify or dissipate that disturbance. We know that humans amplify them. And in this video, as you can see, the second car slowing down more than the first, the third slowing down more than the second. We see an example of a particular type of vehicle where the disturbance is being amplified on the roadway rather than dissipated. Okay, that might not be good for this specific adaptive cruise control system, but it's not a feature of that specific make and model. Basically, every single vehicle that we have tested and now that the community has tested, we all come back with the same findings, that the vehicles have some types of disturbances under some settings that they might amplify. So they're not universal traffic jam amplifiers. And so that leaves us an opening to say that maybe we can ask for more out of our vehicle control systems to try to close that gap between what is theoretically possible, dissipating all types of disturbances, and where we are right now, where some types of disturbances get amplified by these control systems. Well, it's actually relatively hard to get fleets of large numbers of vehicles that one can write control algorithms for. And so kind of in an interim step, we were very interested in this question of like, well, what could you do with the stock control systems on the cars that might enhance the way that human drivers drive? And the idea here is that basically, if we were able to provide drivers with additional information, they might be able to achieve control tasks that we want them to do that could benefit traffic overall. So we had a project with Matt Nice, Safwan, Rahul, Matt Bunting, and Jonathan Sprinkle, where we basically looked at this idea of using the car and using the human to try to do something together that would be better than what human drivers could do. And we focused on speed control or longitudinal control because we know that that can impact traffic waves on the freeway. We know that those waves have environmental impacts. We know that traffic waves in general, high speed variability is bad for safety. So could we somehow combine the technologies and the sensors on the car today, use those to basically effectively coach drivers to become better at some driving tasks? So we're really trying to exploit this sort of connection between the people and the robotic system in ways that might actually allow the team, the robot and the person, to outperform what the robot could do on its own or what the human could do on its own. So what's the punchline? We were able to demonstrate, and I'll show in just a minute, that if you feed back data from the vehicle to the driver and use that to coach them to speed up or slow down, they can achieve some control task better than what a human driver can do on their own. Well, here's what it looks like. We basically take advantage of the fact that these commercially available adaptive cruise control systems with relatively minimal additional hardware can be used to read data that is relevant from a traffic context, like the distance to the vehicle ahead and the relative speed to the vehicle ahead. And that is basically sensors that are already on the car that we can read and then communicate data to the driver to change where they're driving, speed up, slow down, increase the gap, close the gap. And you'll hear more about the hardware involved in this from some of the other talks in this workshop. Just to kind of showcase the essence of what's going on here, basically the adaptive cruise control systems do have a forward-facing radar system in there. And I'm guessing that my, some reason the video is not playing here, but basically we're able to use the stock radar system to get range data, the distance to the vehicle ahead and the relative speed to the vehicle ahead. And we can use that data to tell the driver or identify if the driver is following too closely or too far behind where we'd like them to be. Okay, we're gonna run a series of experiments in which basically the following things are happening. We have a vehicle on the roadway, the driver can see it. The driver actuates the car through, press the pedal on the gas, messages are sent over the CAN, the car speeds up or slows down. And we only instruct the driver, hey, I'd like you to follow the car in front and match the speed of it. Or I'd like you to follow the car in front and I'd like you to match the time separation. I'd like to follow at 2 seconds. Common rule that you might see in driver's ed. Or alternatively, we take the data from the radar sensor that we know the actual distance ahead, we know the speed ahead, and we coach the driver via audio feedback, basically beeping at them, speed up or slow down. And then we watch whether or not this system that is now exploiting sensors from the car and using that to coach the drivers can help the human driver achieve the stated controls task better than they could when we just told them what to do. And then finally, we tried something that was a bit strange. We said, well, is the human actually doing anything? Is the robot actually doing anything? We can find out by getting rid of the car that's in front. In other words, we will synthetically tell the car where we think the vehicle ahead is. The human driver on the freeway won't see it because the car is not there. It's a virtual vehicle, no different than like if you're racing in Mario Kart and you want to race against yourself. They superimpose the image of where you were the last time and you can see if you're ahead or behind. So the only feedback that the driver is getting is audio feedback based on whether we're too close or too far behind the virtual vehicle. That's allowing us to basically differentiate, is the human driver adding anything useful into this loop with their own sensors, their eyes, or is it all coming from the audio feedback that they're receiving? So you get the setup. You can see in the first setting, I'm coaching, I look at the car in front and I see I'm not matching the speed, no feedback. 2, I see with my eyes and I'm hearing with my ears that I'm too close or too far behind, so I adjust my speed. 3rd one, I effectively close my eyes as the driver because the car is gone. It's a virtual vehicle now, and all I'm getting is audio feedback that tells me whether I need to speed up or slow down. Okay, then, basically, to just put a little bit of kind of terminology in what we're talking about here, we're gonna have a vehicle that we're following. It's the lead vehicle, whether it's virtual or real. There's that space gap again that separates our front bumper from the rear bumper of the vehicle ahead and our speed. And what we're gonna be doing is either trying to match our speed V with the leader's speed, V lead, or we're gonna be trying to match the time gap. Basically the space gap divided by the speed, 2 seconds behind, 1 second behind. And we're gonna keep track of what our relative velocity is, and we're gonna keep track of the time gap error. Okay, so the different tests that we're running across the cohort of drivers is basically maintain a constant time gap. For reasons that I can explain later, we chose 2.25 seconds as the time gap that we were asking the drivers to follow. Or velocity matching, we just told them, hey, go whatever speed the lead vehicle is traveling. But hey, either you're going to get feedback that tells you if you're too fast or too slow, or you just do it by your eyesight. And then maybe the most complicated test, we basically said, hey, we want you to follow the 2.25 second time gap, but after a minute, we're going to switch it to 1.8 seconds. And we're going to hold that for a minute, and then we're going to switch it back to 2.25 seconds that we want you to follow. And so in the case where we're instructing the driver what to do, we did beep and tell them when they were supposed to switch from one profile to another, but we didn't tell them whether they're too close or too far behind. Okay, so that's the setup. Again, we've got different modes that we're going to be testing these drivers in. We tell them what to do. We coach them with audio feedback, or we only give them the audio feedback, but we make them follow a virtual vehicle. And the control objective is either maintain the constant time gap, match the speed, or maintain this time gap that is dynamically changing on you once a minute. And then basically we look at what happened. Across 6 different drivers done during a COVID era, we looked at the time gap error when we told drivers to follow a specified time gap. And you can see some of the drivers were all over the place. Some drivers were better than others. When we coached them, everybody got better at the driving task. So it was almost just visually pretty remarkable at how effective giving people information about how close or far away they are from the control objective we're trying to achieve in the time gap was able to significantly improve where the vehicles were actually operating. And to give you an idea of what this actually quantitatively looked like, the average time gap error for the drivers when we just told them to maintain 2.25 second time headway was about half a second. Compared to when we coached them, it dropped to 0.05 seconds. And Matt Nice, the lead author on the study, actually put it really nicely. He said, I mean, if you want to think about a time gap error of 0.05 seconds, take the time it takes to blink your eye and cut it in half. That's the time error that these drivers were able to achieve with audio feedback. So yeah, obviously, it's not a very complicated control task, and it's not surprising that getting feedback is helping you achieve it, but really pretty remarkable in how good that was. Well, when we closed the driver's eyes proverbially and made them follow a virtual vehicle, it actually showed that the drivers were doing a lot of sort of thinking about what was happening in the environment to follow the control task. The ghost mode, where they followed this virtual vehicle, the performance of the control task actually deteriorated quite a bit. That's another way of saying that you couldn't just feed the audio signal into the driver. If you're thinking about this on an open freeway and you want to come up with a complicated control scheme that you want 100 drivers to do, you can't just basically tell them arbitrarily complex control tasks, that say hit some, desired profile of a trajectory I'd like you to follow, because if they can't see the vehicle ahead and have some relative information that they can visually take advantage of to achieve the control task, they do worse than when you're asking them to do something like follow a vehicle ahead, but they can actually see the car that they're trying to do. So it kind of gives us some limitations in terms of the types of virtual trajectories we could follow. Well, CanCoach is one sort of aspect of closing the loop. That gives me a pathway to try certain control strategies with human drivers, because it's hard sometimes to get hundreds of cars that you can overwrite the control systems on, but it's only one piece of the puzzle. The other piece of the puzzle is really trying to understand what the other vehicles on the roadway are doing. And so on a different direction, we've been working very, very closely with the Tennessee Department of Transportation to create I-24 Motion, which will be, I believe, the smartest freeway in America when it's fully constructed in summer of 2022. Basically, we're deploying 300 4K resolution cameras on 4 miles of I-24 near Smyrna, Tennessee. And this video is showing some of the preliminary work from the Tennessee Department of Transportation to put these 4K resolution cameras on 110-foot tall poles that give you videos like what you can see at the bottom, which is continuous overlapping fields of view. You can see vehicles as they pass through the roadway and get the full information about everything that's happening on the roadway. Drilling in a little bit more detail on that system that is currently operational on I-24, 18 cameras, all running at the top of these 110-foot tall poles on a fiber backbone to a building that has a bunch of computers in it that can basically put bounding boxes on the vehicles and track them as they move through this system. That's really exciting for us because as we go from the 18 camera system, which is currently operational, and the 300 camera system, which will be operational in September of 2022, basically we're going to just have an order of magnitude change in the amount of data that we're getting. Many folks are familiar with the NGSIM data set that generated in the Berkeley data set about 1,800 vehicle miles of data, compared to the order of magnitude larger HIDE drone data set that was collected in Germany. Well, I-24 Motion next summer to 2023 over that 1 year block is going to generate about 260 million vehicle miles of data coming off of that freeway. So that's going to just fundamentally change our ability to understand how automated vehicles interact with other human drivers. And really to power this, we're basically going not just nice pictures of cars, but being able to stick bounding boxes on them. And yeah, bounding boxes and images is not trivial, but bounding boxes and images is not where we're headed. What we really need is information that is quantitative. we need to be able to take those bounding boxes, associate them to the exact same vehicle, and generate NGSIM level trajectory data out of this stuff. So you're looking at a video that is less than a day old from Derek Glaudemans and Yanbing Wang, who you're going to hear from later, who basically are now getting us to that level of detail that we're really after, which is basically understanding when we deploy automated vehicles on the roadway, how they interact with the rest of the vehicles on the road. And we can potentially, even if the acceleration and speed data is accurate, be able to feed that into energy models that will ultimately tell us the energy impacts of deploying control systems on the freeway at the level of individual vehicles. Okay, so where are we headed? We know that we can exploit automated vehicles at moderate penetration rates to try to help improve the traffic flow, knowing full well that it's not going to eliminate all traffic congestion problems, but can definitely make a difference in a very important area of eliminating these phantom traffic jams. And we've got technologies that are now becoming available. We'll hear more about the hardware and the techniques that we can use to control vehicles, but I showcased another way that you can actually just use human drivers to control. And really where we're after here is collectively, I think the transportation, the applied math, the computer science, electrical engineering communities, we have a lot to offer here to basically help get these types of technologies on the roadway. And maybe this is kind of the call to action. I mean, we collectively need to work together to find out ways to get this stuff to scale so that we can realize these benefits on our freeways that are desperately in need of them. I'll end there and be happy to take any questions if there is time. Thank you.
Thanks a lot, Dan. So are there any questions? Oh, yes, Alex.
This is a fascinating talk, and thank you, Dan. That was really amazing. Making the assumption that it's not possible to store the data forever, or even to store more than a few days of data, what is the biggest subset of data that could be, quote, conserved forever in a way that is realistic? So you refer to NGSIM, and NGSIM, in a sense, had trajectories. Is there something bigger that can be conserved, or at some point you just run out of space and you just have to have some more minimalistic subset?
And I managed to mute myself on my own answer. Yeah, so I think for sure trajectory is a no-brainer, right? Like if we lose the trajectories, we lose so much relevant context of what's going on the roadways. I think we can do, I'd say, trajectory plus at least. What I'm trying to aim for is at minimum some details about the vehicle type. I'd love to hear from others in terms of what detail would be relevant, but clearly it makes a difference to us whether or not it's a pickup truck versus a small car. With computer vision algorithms, it would be potentially possible to identify makes and models of the vehicle. You got to be very careful. I mean, I'm not interested in building a spy net. I don't want to know that my car drove through that freeway, but I think getting fleet mixes would certainly be relevant. In addition to having the paths and the energy, the tracks that go through. I know from discussions with the team that's really developing a lot of the energy work on the Circles project. I mean, we know that getting good acceleration data on there is non-trivial, but also really important to getting good energy estimates. So I think that's another natural area to expand on. I think bluntly, it's going to be impossible to store 300 streams of 4K resolution video data for any useful amount of time, just because the data rates on that are insane. We're talking about a 40 gigabit per second connection from that system back to Vanderbilt to be able to process that data. And we're basically going to be processing it as fast as we possibly can because we can't afford to buffer it. It's just too big. But yeah, I'd love to hear wish list and dreams of like, well, if you were only able to save this or store that or compute this other thing, this would be, game changing in terms of my own research. The worst thing we can do is actually try to figure out whether or not it's technically possible. The system has not yet been built, so now is the time to weigh in with a type of input that would make it useful for you.
Thank you.
Okay, so I do have a question, but that's very specific. When you were talking about giving coaching to drivers, so I understand that the more information you give them, the best it is for the stimulus. So if you give both audio and visual feedback, and if they have visual feedback, then it's going to be better and they can achieve amazing performances. But what's the best between when they have only the audio feedback and when they have only the vision?
That's a good question. I don't have it off the top of my head, but I'll look it up. I know we have that data. I just don't remember actually doing that comparison. So I'll look it up in our data and get back to you. But it kind of makes me think on another line here that's an important piece to clarify. This was not a human computer interaction study. The feedback we provided was rather aggressive beeping. I think we could probably significantly further improve the performance of what the human drivers are able to achieve with the feedback by optimizing that feedback in a way that's the least distracting as possible and communicates enough information. Yeah, my guess, and it's an open one, is that probably the right feedback designed intelligently would be potentially better than human feedback alone, with maybe the exception that speed matching human drivers, I do remember from our data, they were pretty good at maintaining constant velocity. So there might just be some control tasks that the humans are better able to perceive than others. Time headway is just harder to interpret than drive the same speed as the car ahead.
Yeah, I guess so. Okay, thanks a lot. Are there any other questions? Okay, otherwise we'll have a 15-minute break and we'll resume at 2 p.m. Eastern. Is it? Yeah.
Okay, thank you all.
Thanks a lot. All right, so see you soon, everyone.